Hello, so welcome everybody. This is the first tutorial we've had for Intro to Stats. Until Easter it's half tutorials, half labs. I was kind of half expecting Sarah Lees to be here because he said he was going to act as my TA. So for the time being we don't have a teaching assistant. So my name's Jenny. You can call me whatever you like, or you will do. My email address is on there. I've got an office hour, which is later on today on Thursdays if you want to come by and ask any questions. You can also, of course, go to Sarah Lee's office hour. He's very friendly like that as well. Everything you need, it should be accessible via the Blackboard page. I realised that for this course, if you go to the Blackboard page, it redirects you to Sarah Lee's personal website, but it's all still accessible there. So the only other thing I wanted to mention, there's more things. So the first thing I wanted to mention was that we're going to use my Poll Everywhere page occasionally. When I'm showing a question from Poll Everywhere, how to get on it is on the top of the question, but it's also there as well. The general format for all of my tutorials this semester is the same. So you're going to start off with an introduction. Hopefully it's going to be shorter than this week's, and there's going to be a poll so that you guys can tell me which one of the questions you'd like me to go through on the visualizer first. So I'll do one or more example depending on how long the question is that you choose for me to do. We're then going to have some free time for you to work on anything that you've not done on this exercise sheet yet, maybe with the person next to you or just on your own, however you prefer. I'll circulate and answer any questions. If Sarah Lees is here, he'll do the same. I'm expecting that to take about 20 minutes. And then during that free time I might pick a question from the exercise sheet and say, if you've not done this one, work on this one. We might have the summary of another solution to one of the questions on the exercise sheet at the end. I don't think we're going to get around a repetition because I've barely got through this once during most of my sessions. So number 6 is please interrupt and ask questions or clarifications. I find this really, really helpful, and you'd be surprised how easy it is to make really silly mistakes when standing in front of nearly 100 people. So if you see something you're just like, oh, this lecturer just can't differentiate, just let me know and I'll correct it. And finally, make sure you register your attendance. It's important. Well, it might be important. It is important. Register your attendance, okay? So, here's my Poll Everywhere question, which is, which question would you like to see? So I'm going to give you a few minutes to respond to that. We should see the responses come in live. So these are a little bit too low. You see where to go now?
明天中午11点对这个什么馈赠。
I guess my question is question 7 popular because only one person voted, or is it popular because everybody agrees? Okay, so we've got 3 responses. Everybody thinks question 7. Let's try and get a few more than 3 responses. You're also allowed to click more than one question, so I've set it up so you can click as many as you like. We've got fairly evenly distributed preferences there. That's interesting. So seeing as question 3 and question 4 are very, very similar, shall I maybe do one of them? Because that would satisfy everybody who wanted question 3 and question 4. And then maybe at the end we could do question 7. Okay. Okay, let's try that. Right, that seems to be the one that works, the one on the right. Right. Okay. So, question 3. And I'll try and compare and contrast with question 4 as we go through so that you know what's going on. So we were given a sample of 5 numbers. And this is the population that we're going to randomly select from. And the first part of the question said, what's the population mean? In this example, it seems like that's not great. It seems like we know what the entire population is, so calculating the population mean is not a problem. We just need to take the mean of these 5 values. And I'm hoping that you remember from high school that when you take the mean of something, you just add them all up and divide by the number that there are. So the population mean is 6. The second part said, what are the moments of one element selected at random? So I'm going to introduce a random variable x1. And x1 is going to represent me selecting one of these 5 elements at the top randomly. Because each of the numbers only occur once in the sample, it's okay for me to assume that each one is selected with equal probability. So x1 is a random variable taking a value in the population set with equal probability of picking each element. it's a discrete random variable. So the expectation of x1, what do I expect that to be? Well, exactly the population mean, because I've got equal probability of picking each element. So the second thing I was asked for was the variance, and the easiest way for me to get there is to first of all find the expectation of the second moment of x1. So you'll remember from probability 1, if I'm finding the expectation of a discrete random variable, a function of a discrete random variable, what do? I'm going to sum up the possible outcomes and then weigh them by the probability that x1 takes each of those values. So I just need to square each of the elements in the population, add them all up and divide by 5. And then to find the variance, I need to combine these two. Right. In the end, I get 10.8. So I think the tricky part of this question was actually number 3. In number 3, I was asked, what are all of the possible samples of size 2? What's the sample mean for each of these samples of size 2? And what are the distributional qualities of the sample mean in each of these cases? So the first thing I needed to do was think about which permutations could happen. So I decided to set myself up with a table. I decided that in the rows I'd put the value of x1, okay? In the columns I'd put the value of x2 that I picked. And then in the body of the table I'd put the sample mean for that particular case. So we'd have 2, 3, 6, 8, and 11. 2, 3, 8 and 11. Okay, so for example, in this first box here, my sample of size 2, I select 2 twice. So the mean of those two together is going to be 2 plus 2 divided by 2 is 2. Similarly, here, the first member of the population I pick is 2. Second one is 3. So the mean of these two is 2.5. And I'm going to continue like that to populate the table. And hopefully you've populated everything in there. So once you've got those, we now know the possible values of the sample mean as a random variable by looking at all of the numbers that are in this table. So the possible realizations of the sample mean, I'm going to use a little x because they're the possible realizations rather than a random variable, are going to take values that I'm then going to put in a table. Like this, okay. And the other thing I want to put on there is the probability that the sample mean takes that value. Okay. Now, once you've filled out this table here, you'll see that the only place where there's a number 2 is in this top corner here, and that there's 25 values in the table overall. So the probability of me picking a sample which has got mean 2 is going to be 1 over 25. Similarly, with 2.5, that only occurs here and here. So the probability of that one happening is going to be 2 over 25. So it's the frequency with which they're in the table divided by the total number of elements in the table. And then you can check that you've populated this table correctly by making sure that the entries that you put in the probability row add up to 1. Okay. And once we've got a table like that, in order to find the mean and the variance of the sample mean, we need to use this data that we've just constructed. So the mean of the sample mean is going to be again a sum over the possible values of the sample mean and the probability with which they occur. And what we're going to be doing is we're going to be multiplying this value by this value and then adding on these two multiplied together, etc., etc., etc. And you should get yourself to 6. And then with calculating the second moment, you're going to be doing something very similar, but you've got to square each of these values. And you should get yourself to 41. And from that you should be able to calculate your variance of x bar. Okay, so I'm going to leave that final little bit of calculating to you. Okay, so when we changed the question to without replacement in question 4, we just need to go back to our table at the beginning of part 3 and notice that we're not going to be able to select this outcome here is not going to be possible without replacement, because once I've decided what the value of x1 is, I've decided that the value of capital X1 is 2. When I come to select the second random variable, 2's gone from the sample. I've only got the rest of them to pick from. So I'm going to use exactly the same approach. Okay, so exactly the same approach, but this entry is not possible. 3 is also not possible. 6 is not possible, etc., etc. All of the other values are the same. And we notice that there's a symmetry around that lead diagonal. So when we come to filling in the table here, we're going to have 2 divided by 20 for most of the elements. There is actually one that occurs twice. So yeah, they're not all 2 divided by 20. There's lots of 7s in that table. But we do get this symmetry, and we can proceed in exactly the same way. So quite a lot of the probability is simplified to something over 10, 1 or 2 over 10. And we can find the mean of the sample means and the variance of the sample means in exactly the same way. So, is that clear? Would anybody like to ask anything about question 3 or question 4? Okay. Well, I'm going to assume that there might be some questions, but maybe it's a bit scary to shout out in front of everybody. I've got a little bit of a question, just one kind of quiz question, just to double check if you guys can understand how this is working. So here's the question. So more than one of the answers is right? So what does it actually mean for the sample mean to have a distribution? And the reason why I'm asking this question is because when I was an undergraduate, even though it is like possibly around the time you guys were born, I had exactly this question, and it burnt inside me for nearly the whole way through my elementary stats course, and it took a long time to bed in for me. So I'm asking it now just to see who else kind of has the same level of frustration with it, or just this kind of conceptual struggle. So what does it mean for the sample mean to have a distribution? So read the 4 statements and see what you think. Give us some feedback on what you think. Oh, and if loads of people pick D, I'm really happy with that as well, because, you know, I just think that's the answer I had for such a long time. Okay. Okay, so lots of people are choosing that third option, and a few people are saying we don't know. I think that's reasonable, right? Note that another thing you can do with this is, if you're not feeling very confident, you can see what options your peers are going for, and you can pile on whatever option they've selected. You're also allowed to change your mind as well. So, you know, if you've selected one, if you're on the website and you're like, oh no, I picked the wrong one, you can pick another one. It's not a big deal. Okay, so let's have a look. Yeah, responses. Right. In terms of correctness, both of the middle two were right. Okay. Now, definitely the third one. Definitely the third one was the most rigorous statement. It says, a sample is a collection of random variables, so the sample mean is a random variable with a distribution itself as well. That's the most rigorous way to understand it. Number 2 is also right. So we don't know what the observations in the sample will be, so we don't know what the mean is until we've taken our sample. It's also kind of right. It's not wrong. The first one's most definitely wrong, and the fourth one's just an admission that things are kind of tricky. And even number 4 has some truth in it. So the mean of some random variables should be a number is true. But we don't know what random variables we've picked. So it's a random variable until we've actually selected one particular sample. Okay. So I wanted to leave you guys for maybe about 20 minutes just to work on something on the exercise sheet. If you've not worked on exercise sheet, question 7, please do work on question 7 until 22. If you're stuck, maybe speak to people next to you, that sort of thing, raise your hand up, speak to me, and then we'll come back with 10 minutes to go and I'll show you number 7 on the visualizer as well. So, here's number 7. take a look at this together. Let's go for... Question 7. So we've got lots of realizations that have the Poisson distribution. We've been told that for each I in my sample of size 5, that realization is Poisson distributed with parameter lambda. Now I'm able to say this because they're identically distributed. That was sort of in the way that the question was phrased. And it's kind of important that they're independent as well. Now these are some of the key assumptions of sampling data that we use in this course. And I can think of lots of real life examples where observations wouldn't have these properties necessarily. So maybe as you're going through, kind of think about what kind of things you're actually going to want to use statistics for, and whether these assumptions that we're using for the time being of identically distributed and independent are realistic. Okay, so we've only got one sample of observations, with 5 elements, and we've been asked to find the joint distribution. So what we've been asked to find is the probability that x1 takes the value 9, x2 takes the value 13, etc. Oh, there's actually 6 of them. Well, okay, so we've been asked to find this probability. Now this looks really, really horrible and messy, but we're lucky that we've been told that they're independent. Because of the independence, we're allowed to write this as the product of the individual probabilities. So we're allowed to write this as px1 equals 9 times the probability that px is equal to 13, etc. So multiply them together like this. And that's only possible when we've got independence. Okay, so this product, I can write that in shorthand like this, with the product symbol, and I'm going to multiply from 1 up to 6, because I've got 6 elements. The probability that xi is equal to little xi. And what are they? So the capital Xi is the random variable that is Poisson distributed, and the little xi is the element in the vector that I've been given. So xi1 is 9. So little x1 is 9, little x2 is 13, etc., etc., etc. So now I've got something where I can apply probability 1, 2, because there's only one random variable in each of those terms in the product. So I kind of remember from probability 1 what the distribution function for a Poisson distribution is. It's something like this. I still need to do the product, of course. I should put lambda xi e to the minus lambda, and then divide by xi factorial. Okay. So I'm going to need to simplify this beast a little bit. So the first thing I can recognize is that if I'm taking a product, I can take the product of the stuff on the top of the fraction and the product of the stuff on the bottom of the fraction. So I can split it like that. Now the next thing I want to notice is that the factor e to the minus lambda is a constant, so I can put that outside of the product. And if I'm multiplying together lambda raised to the power of x1, lambda raised to the power of x2, etc., I can switch that to a sum. Okay. Well, actually, I'm going to have 6 of these, aren't I? Okay, so now I've got an expression where I can plug in the 2 values of lambda and I can compare which one is bigger. So if lambda is equal to 10, then I put lambda is equal to 10 in this expression, and the joint probability is going to be Mm. 5.907 times 10 to the minus 7. So it's really tiny, but I'd kind of expect it to be really tiny, because if the number of possible values of a sample of size 6 of the Poisson, with each realization Poisson, the space is really, really massive of possible outcomes. So I'm expecting the probability of one particular outcome to be low. So I'm kind of expecting it to be low, and I've got this value. And if you take the other one, so if lambda equals to 12, you plug your 12 into the expression star again, you get 1.704 times 10 to the minus 7. And we can see there that it's more likely that we get this particular combination of outcomes with the parameter lambda is equal to 10. So we've got a little tiny bit of evidence to suggest that it's more likely that the parameter is 10 than the parameter is 12. Now we can't really draw any conclusions because they're very, very small numbers and we've only got one sample, but we're sort of going in the direction of how we might decide what the parameter is. Okay, so perfect, I've got 1 minute left. And what I wanted to do with my 1 minute left is to ask you guys another question, which is, how do you feel about completing the rest of the exercise sheet now that you've had a little bit of an explanation from myself? Let me know on there. Otherwise, I'll see you all next week in the lab an hour later. The lab is 11.
就是它没有后面的参数的话，你去做这个收尾答题，它有你为了把它变成最高
它不只是中广表面。
看来用它的目的先教我，然后先教我，一共就34。
哦，是的。
两个 DVD，咱们医生包不是咱俩门口买的肉的，我做饭，还有2个小时。好吧，我正好把这2个吃了。下面就是。
I was ill last week, so I missed the tutorial. And I was just wondering what was covered in it.
So we had a computer lab before after.
姨夫肯定困困的想睡觉了，所以他这样。
Gave us a really long explanation of what to do in that lab. It's not really too difficult because you just read through.
做了1个多小时，这个意思。
What I hope that you could do after reading through is load up on one of the computers in the lab.
Okay.
Yeah? Do some basic calculations. It's a bit like a calculator.
Right.
Define an object. So say that x is equal to 5 or x is equal to a vector.
就开始说瞎
And
话。
then do some stuff about operations on vectors.
看这个人就喜欢说胡
And
话。
loaded it with information
面。
from Sarah Lisa's website. And most of us only got a question through.
我要以前
So what we were doing is we were just checking, load some data in, because obviously loading some data in.
也是。
Yeah.
So that's where we got to. So if you just take a look up to there yourself, and then next week, if you want to continue with this one, that's fine. Want to look at the next handout, which again will step you through everything. That's great. And just ask anything you need. Both me and Carol will be there to make sure nobody's got any.
Here we are.
Yeah. It's my experience of labs, and it's just me, obviously. You can see from the question that I put on the board that I'm a bit dumb sometimes. As a student, was my experience of labs was always like, you know, everybody's going together, and then you get 15 minutes in, and your computer doesn't do something the same as everybody else does, and then you've lost half an hour because you just sat there, like going, I don't do what I want. Yeah. So we're going to try and avoid that.
Okay.
At all costs.
Awesome.
All right, is there anything else I can help with?
No, I think that's everything.
Was everything clear today?
Yeah.
Was it good? And that's great, that's great.
Thank you.
See you soon.
Have a good day. Excuse me, can I have a couple of pieces of paper I can borrow? Excuse me, can I have a couple of pieces of paper I can borrow? I've completely forgotten my
Just one paper or just the notes?
just the notes.
Something ready to?
Yeah, yeah. Thanks very much.